In this video, we're going to go through section 5.4, which is mainly on the indefinite integral, but we're also going to talk about the net change theorem. All right, the indefinite integral. So you've got the definite integral, and then you have the indefinite integral. Now, in previous videos, I've talked about both of these types of integrals, as well as the general meaning of the term integration, and I'll go ahead and give another full summary of all of that here as well. Okay, so here's the indefinite integral, and as you might already be familiar with, the indefinite integral is a symbol to indicate find the antiderivative of the given function. Now, if you're like me when I first went through calculus, once I was done with calculus, the term antiderivative was pretty much erased from my mind and replaced with integrate. To me, if I used the term antiderivative in any circumstance, that would be I would look stupid. Why are you saying antiderivative? It's integrate. However, what I've come to learn is that, so in my opinion, if someone has the term antiderivative just erased from their mind, then that shows that they really don't have a full grasp of the fundamental theorem of calculus. Okay, and so as I've mentioned before, reading through this textbook and doing other research, it seems to me that the term integration, was first introduced purely in association with infinite summing, the infinite summing process. So we first talked about, we looked for a method to find areas under curves. We broke the curves up into approximating rectangles, then took the limit as the number of rectangles went to infinity, and then summed those infinite number of rectangles to find the area. But we're going to see as we progress through calculus that this infinite summing technique can be used for all kinds of applications outside of just areas under curves. So like to find lengths of curves, volumes, all kinds of things. Okay, and so here is this. I'm not looking at this as a tool for determining areas under curves. This is an infinite sum tool, an infinite summer. And so you're summing 1 to n pieces as n goes to infinity, where each piece you're multiplying the function that you're dealing with, evaluated at any point within the interval you want, left endpoint, right endpoint, midpoint, whatever, or some mixture, because because the point you choose within the interval doesn't matter as n goes to infinity. Everything converges to the same point, to the same value. Okay, so the function evaluated at any point you want times the width of each interval. It's the same width for each interval, delta x. This is that infinite sum tool, the infinite summing process. This is what the term integrate is all about. The term integrate or integration first came about and really is all about this here. Even currently, it's really all about this infinite sum tool, the term integration. Okay, and after this was fully developed, a notation was created to represent this that was more compact and concise. So the sum symbol, along with the limit as n goes to infinity. So you call it like an infinite sum. It's not just the sum symbol, but also taking the limit as n goes to infinity. This was replaced with this elongated s symbol, the classic integral symbol. Now, every single infinite sum process is associated with an upper and lower limit. The infinite summing makes no sense if there's no upper and lower limit. So you also put the upper and lower limits here. B is the upper limit, A is the lower limit. Okay? Next, you put the function, the associated function, because every infinite sum has an associated function. But remember, as n goes to infinity, as far as what, like the endpoints you're using, left endpoints, right endpoints, whatever, it makes no difference. So you just put the function. That's it. All you got to do is put the function. And then for the delta x, you put dx. Why dx? Because as n goes to infinity, delta x becomes infinitesimally small. And so it takes on the same symbol as for the derivative, the dy dx. These are as large as infinity is as small as dy and dx are. So it's the same idea. When you take, for the derivative, when you take the limit as h goes to 0, the delta y and the delta x become infinitesimally small. And so that's what dx is. Okay, and so this is the symbol that was said to represent this infinite sum tool, the more concise, compact symbol. Okay, now what you can imagine is once they had this infinite sum tool invented, they were looking for a way to evaluate the result of the infinite sum as quickly as possible. You know, because it's kind of a drawn out process to evaluate this. So maybe they were looking for some shortcuts. And so the way I imagine it is, I don't know if this is exactly how it went, but the way I imagine it is, I'm sure they thought they could come up with some kind of shortcut. But as far as what the shortcut was going to be, they had no idea. The fact that, as we know from the fundamental theorem, the shortcut is associated with differentiation, but in the form of antidifferentiation, that didn't have to be the case. So I don't imagine that when they were developing this tool that they had a sense that, oh, wow, well, antidifferentiation is going to be associated with this. I mean, they might have. I don't know, but I'm just trying to give you the idea that there's no, you don't, when it comes to the fundamental theorem, you don't think about there being any inherent association between differentiation and integration coming into calculus. That was like, you think about that as like being discovered. That's the idea. Okay? And so, but they discovered that to evaluate this in a quick way, you can find the antiderivative of the function, which we will write as capital F, evaluate that at the upper limit of integration, and then subtract that from capital F evaluated at the lower limit of integration. All right, so once this was discovered, once this shortcut was discovered, what you can think about is that when it came to finding antiderivatives, they were called antiderivatives. There was no notation to represent, to say find the antiderivative of something. What I mean is, so if we want to say find the derivative of x squared, how do we say that? Well, there's different ways, but one way you could write it is like this. This means find the derivative with respect to x of x squared. But at the time, there was no way to write find the antiderivative of x squared. And so what they decided to do was, because of this association they discovered between integration and antidifferentiation, they decided to say, well, let's go ahead and use this same symbol here. What we'll do is we'll put this symbol, don't put any limits of integration, put dx, and this is going to be the symbol to say find the antiderivative. This means the antiderivative of x squared in the same way that this means the derivative of x squared. Okay, now this could be confusing because you wonder, well, is this like an infinite sum? It's got the infinite sum symbol. This has nothing to do with the infinite sum process, this integration process. Mathematically, yes, but application-wise, this has nothing to do with infinite summing. This literally just means what is the antiderivative of x squared? That's it. This means 1/3 x cubed plus c. So this is the most general form of the antiderivative of x squared. You use this symbol in differential equations, right? These two applications are very different. It even notes here in red how the result of this antiderivative here is a family of functions, a whole family of curves, as opposed to the result here of the infinite sum integration process is a number, like 1, 2, 3. Okay, now, so they introduced this as the symbol for antidifferentiation, and also they put this under the name integration as well. So they gave this the integration symbol, and this was also put under the name integration as well. This was termed indefinite integration, and this was termed definite integration. And so that's why the term antiderivative it kind of gets phased out and replaced with integration. Okay, so again, the infinite sum tool, which to me is the heart of the term integration, the infinite sum tool is called the definite integral, and the symbol for the definite integral is as shown here. The symbol to represent find the antiderivative of this function, which because of the fundamental theorem has been given the name indefinite integral, as well as a symbol associated with the definite integral, is as shown here. Here is the indefinite integral. This means what is the antiderivative of this function. So over the course of this video, and as we get into the upcoming videos, I'm going to transition away from using the term antiderivative. I'm just going to say integral. But so we've just been introduced to the indefinite integral. And what the rest of this section is about is we're going to go over the basics of evaluating an indefinite integral, i.e. the basics of finding an antiderivative. And so they start by, they give a table of indefinite integrals. And so we had a similar, more condensed table like this in the last section of Calculus 1, which is on the antiderivative. But we didn't work any practice problems there because I knew that we could just wait to work with antiderivatives until we got to this section. Okay, so now we're starting our journey here on learning how to find antiderivatives. We want to get as skilled with finding antiderivatives for all kinds of scenarios, simple and complex, as we got with finding derivatives in Calculus 1. So these are tables of indefinite integrals. These are integration techniques. Okay, so the first two here, if you're integrating a constant times a function, then you can bring the constant outside of the integral and then just find the integral, the antiderivative of the function without the constant. Okay, here, if you're integrating the sum of two functions, then you can separate that sum into two separate integrals. And this is plus or minus. Okay, if you're integrating just a constant, that's it. The function is equal to a constant, then the integral is the constant times x plus c. And this makes sense. What's the derivative of kx plus c? Well, we know that. That's just k. C is 0. The derivative of c is 0, and the derivative of kx is k. Okay, now here's the power rule for integration. It's just showing, it's the idea that when you're integrating x to some number, it's like the reverse power rule. And then also here's the integral of 1 over x, which is the natural log of the absolute value of x. And it should be the previous video, I talk about these two integrals. I talk about why is the integral of 1 over x equal to why is it the natural log of the absolute value of x? Where does that come from? And is it necessary to put the absolute value every time you do this integral? And I talk about how the power rule for integration is kind of associated with the integral of 1 over x. Okay, now, and so all of these, it's pretty much like it's common sense. These are basic functions. Like the integral of e to the x is just e to the x. The integral of b to the x, what's the derivative of b to the x? It's b to the x times natural log of b. So the integral would be b to the x over natural log of b. Because if you take this derivative, you just get b to the x and then put the constant. All right, so most of the integrals that we're going to look at in this section, we can reason through these integrals on our own based on our knowledge of differentiation. Right, so like you could be given a power and not necessarily need the power rule of integration to find that integral. You could just reason through, okay, well, since I know how the derivative of like x to the 5th works, then you can kind of just mentally go backwards to figure out what the integral would be. Okay, so again, based on our knowledge of differentiation, we probably in the back of our minds already know or could quickly figure out these integrals. But we can still reference this table if need be when we're working example problems. But what you can imagine is after this section, the integrals are going to get more complex. So what if you had sine squared of x? What if you had x times e to the x? And so we're going to need techniques for evaluating the integrals of more complex functions. But in this section, we're just working with the basics. All right, so it says, recall from theorem 4.9.1 that the most general antiderivative on a given interval is obtained by adding a constant to a particular antiderivative. We adopt the convention that when a formula for a general indefinite integral is given, it is valid only on an interval. Thus, we write, so, yeah, so to me, this is, fancy math talk. But what they're saying here is that, so when you look at this indefinite integral, you agree that, so the indefinite integral, the antiderivative of 1 over x squared is minus 1 over x plus an arbitrary constant. Okay, that's right. However, when you think about this, so you can't divide by 0. And so what you have is you've got two separate intervals here. You've got an interval to the right of x is equal to 0 and an interval to the left. And so what happens is you've got kind of two separate curves is what they're saying. You have an integral curve to the right of x is equal to 0 and also one to the left. And so the convention that they're saying that the textbook is going to adopt is that when an indefinite integral is specified, you're really thinking about each interval separately. And so the more technical way the textbook would write this indefinite integral here is like this, to where you've got, if x is less than 0, you've got minus 1 over x plus c1. If x is greater than 0, you've got minus 1 over x plus another c2. Like the c's don't have to be the same. So you could have one curve, you could have minus 1 over x plus 7 for x is less than 0, and then you could have minus 1 over x plus 50 or minus 30 for x is greater than 0. Both of those, the derivative of both of those results in 1 over x squared, right? So they're both valid indefinite integrals, right? So like if like for a actual real application, you could evaluate the indefinite integral, and in differential equations, you're going to see these constants. You find constants like this based on boundary conditions. So like a boundary condition is like, what's the starting position when time is equal to 0? And depending on that starting position, that's going to constrain what the constant is. And what they're saying is that you can find this integral, and based on the boundary conditions, you could use two separate curves in the two intervals. That's what they're trying to make clear. Like, C, you don't have to you're not constrained to just choose one C for the entire domain of the antiderivative from minus infinity to infinity. That's what they're saying here. Okay, so next they go into example problems, just finding indefinite integrals. And we're gonna, in the next video, we're gonna work a bunch of these. Okay, so this section also talks about what's called the net change theorem. And so what this is saying is that I can try and summarize this for you, because I feel like mathematically it's hard to look at this mathematically and get an intuitive sense of what it's saying. So this idea here, this net change idea, this works for any independent variable, but it's easiest to initially illustrate if we consider the independent variable is time. And so, okay, if let's say we have any function that is some kind of rate of change, which means that it's, in some sense, it's a change in some quantity with respect to a change in time. So again, we have a function that represents a change in some quantity with respect to a change in time. Like, for example, velocity. That's a change in distance with respect to a change in time. Or acceleration. That's a change in distance per time with respect to a change in time. Okay? They give more examples here, like concentration, a change in concentration with respect to a change in time. So anything, right? So you have a function, though, like a velocity function, an acceleration function, I don't know what you'd call this, a change, the derivative of a concentration function, I guess you'd call it. Okay, so you have any rate of change function. So we're focusing on the independent variable being time at the moment, but it doesn't have to be time, but that's what we're focusing on, time to illustrate this. All right, what the net change theorem says is that if you take the definite integral of that rate of change function over an interval. So now we're talking about that infinite sum tool. When we talk about definite integral, we're talking about the infinite sum tool. Okay, so the definite integral, you have your rate of change function, rate of change of some quantity, it could be anything, some quantity with respect to time, and you're going to evaluate the definite integral of that rate of change function over an interval. Then that definite integral, what it's equal to is the net change in that quantity over the same interval. The net change in the quantity. So for example, velocity. If we're taking the definite integral of a velocity function over an interval, so a velocity function is it's a change in distance with respect to a change in time, okay, over an interval from A to B. Again, the definite integral of the velocity function, it's a rate of change function. Rate of change of what? What's the quantity? With a velocity function, what's the quantity that's changing? It's the distance, okay? So the definite integral of the velocity function over the interval from A to B is the net change in the quantity over that same interval. And so the quantity would be the position. I mean, so I said distance here, but it's more of the position. The velocity function is the rate of change of the position with respect to time. So the definite integral of the velocity function is the net change in the position over that interval. So, and what does net change mean? Remember, net change is you can have, if you're starting at A here, you could do all kind of crazy stuff from A to B. The net change is just the function evaluated at B minus the function evaluated at A, and that's it. It makes no difference what's going on in between. Okay, so if you're integrating the acceleration function, so what's the quantity that's changing in the acceleration function with respect to time? It's the meters per second, the speed, the velocity. Right? So if you're integrating the rate of change function, the acceleration function, where the quantity is velocity, that's what's changing with respect to time. So you're doing a definite integral of the acceleration function over an interval, then that's the answer to that is going to be the net change in the quantity, which is the velocity over the interval. And this makes sense, right? Because if you right? So the definite integral from A to B of an acceleration function, well, what's the antiderivative of the acceleration function? It's the velocity function. And we know how to, based on the fundamental theorem, so it's VB minus VA. This is the antiderivative, so just plug in V of B and subtract from that V evaluated at A, right? But I want to stress, though, again, it's any kind of rate of change of any quantity with respect to time. So here they've got the change in concentration with respect to time. So that definite integral is going to be the change in the net change in the quantity. So what was the concentration, the actual concentration at time t2? Subtract from that the actual concentration at time t1. That's the net change theorem. And so to illustrate this, we used the independent variable time, because that's the easiest way to illustrate this, but you can mentally try and extend this to any independent variable, because this theorem is valid for any independent variable, not just time. Okay, now it gives an example here. It says if we want to calculate the distance an object travels during a certain time interval, and so this is going to be the total distance traveled, not the actual net displacement. Right? So initially, they thought about the idea, what it talks about is the idea of, so a particle moving in a straight line, it can go in the positive or negative direction, left to right. And so the result of the definite integral is just going to be the position at the start minus the position at the end. And even if the object moved a lot, that definite integral could be zero if the object starts and ends at the same position, the integral of the velocity function, right? Because again, the net change, it doesn't matter what's going on in between the endpoints, right? And so they're saying, what if we want to consider, even if the object ends up at the same, it starts and ends at the same point, but it did a lot of moving in between. What if we want to calculate the total distance it traveled in general, right? So it starts here, it does all kind of stuff, and then ends up at the same spot. But we still want to calculate how far it traveled overall, even though it starts and ends at the same spot. And to do this, the idea is you would take the absolute value of the velocity function. You would find the definite integral of the absolute value of the velocity function. So that way, instead of subtracting out distances that are going in the negative direction, you're just adding those distances traveled in opposite directions. Even if you have distances being traveled at a certain speed in opposite directions, those are still just adding to each other. You're not subtracting, with the regular integral, without the absolute value, you travel a certain distance in the forward direction, and then you'd subtract any distance traveled in the reverse direction. What you're considering for the definite integral, you're considering speeds in the forward or reverse direction. That's the function you're integrating. But if you integrate the absolute value of the velocity function, then even if you're going in the reverse direction, you're just adding the distance associated with that velocity. And so it says, so if you're just integrating the regular velocity function, then this is the displacement, right? The net displacement. This could be 0 if you start and end at the same spot. But if you're just getting the total distance, then they're just adding up the areas under the velocity curve instead of subtracting some of those areas. All right, then they work a couple of examples, but we'll do a bunch of examples on the net change theorem in the upcoming videos.